All right, thanks Greg, for the presentation. So next up is Coverston from DataStax, who will talk to us about Cassandra. Just take a poll. How many people before tonight had heard of Cassandra? Wow, nice. You guys all can tell me who open sourced it. Little startup called Facebook. Okay, so looks like it's ready to go. I'll turn the time over to Ben. Thank you.
All right, this is Courtney. So, by way of introduction, my name is Ben Coverston. I work at DataStax. I have some lofty title, but really what that means is that I get to deal with all the stuff the CEO doesn't want to do, and sometimes he lets me code. So, people have already asked, we've already asked the question, who's heard about Cassandra? Is there anyone in the room right now who actually uses Cassandra? All right. I guess I'm the expert in the room then. So, let me just turn this on. All right. So, a little bit of history. Cassandra was open sourced by Facebook in July 2008. It was implemented as the solution for inbox search at Facebook. It was basically a little project done by 2 people there. When they were done with the project, they threw it out and they said, here you guys, in the open source community, here's this little project that you can play around with. We call it Cassandra. And so it just sat out there for a while, and it ended up in the Apache Incubator, where a friend of mine and a friend of many people here, Jonathan Ellis, who was working at Rackspace, picked it up and started working on it. And as he was working on it in Rackspace, it got better and better. Finally graduated from the incubator in March of that year, or of the next year, excuse me. And then we founded Riptano in April 2010. Later we changed our name. So then we had our first summit in August of 2010. And then later, like I said, we changed our name to DataStax in January of 2011. And we just had our latest summit in San Francisco. We had great attendance. There were like 450 people in attendance, over about 150, generous estimate of 150 the year before. So we're off to a running start. The community is growing. So why did we change our name? So the suits, they didn't like our old name for marketing reasons, maybe relevancy. They said Riptano was too skateboardy. The reason I think they changed the name is because DataStax has an X in it. And Bender Benny Rodriguez in Futurama basically said, hey, I don't like the word blackmail, it sounds dirty. I like to use the word extortion, and it sounds cooler because the X makes it sound cool, right? So that's basically why I think we changed the name, because you spell something wrong, you put it on a t-shirt, all of a sudden it's awesome, right? So why use Cassandra? Cassandra is scalable, it's reliable, it has replication that works, naturally supports multi-data center applications, there's no single point of failure, and you can have analytics in the same system that you do your online transaction processing. You don't really have to ETL your data to do analytical workloads on your data, which is quite nice. What are the weaknesses? Well, what are the weaknesses of most NoSQL systems? Well, you start partitioning. We talked about the cap theorem earlier, so I won't elaborate too much on that. But as you start partitioning your data out, and you start making trade-offs between consistency and availability and partitioning, you lose that pony. ACID is something that you can't that can't really come along with you. So when you started to shard your data, as your data got larger than a single box could really handle, and your working set got larger than a single box could hold in memory, you kind of lost that ability anyway. So a little bit of history about why NoSQL became kind of a big deal. Again, we already talked about this at some length, but relational databases generally scale poorly. They scale up pretty well. They don't scale out as well as they scale up. B trees are kind of slow, and they require a read before a write to be useful. And with a relational database, I hope your working set fits in memory, because if it doesn't, then you're screwed anyway. So what's our first attempt at scaling, right? The manager gives us some money, and we put a server in there. And then if we need to make it go faster, we just buy a bigger box, right? And if having a bigger box doesn't help us out, then we have some machines and maybe we add a caching layer in front of that. And then if that doesn't work, maybe we add a couple more databases that do different things. So we start partitioning our data out. And then as our individual databases grow, then we start sharding those out. Then somebody comes to us, an auditor or whoever, and says, what are you doing to back up your data? So you start adding more machines even there. And then you decide it's slow again, too slow again, so you add another layer of abstraction in front of that. So you end up with multiple layers of caching in all of these databases and their associated backups. So what do we end? Sorry about that. So what do we end up with? So in December of 2002, this is basically what eBay's data model looked like before they really started looking at going to some other type of architecture. You can see they've got major databases to do a couple of things here, but the category databases are really what they've sharded out. So they're basically taking different categories that people might search on, and then they've separated them into separate databases, each with the main store and another replicated database. So they end up with something that looks nothing like what we would consider a traditional relational database or relational database model. They sharded their data up. It's made it difficult to actually use and deal with. So they end up with something that at some point, it gets to a point where it's hard to maintain and you're afraid to change anything, basically illustrated by sort of this thing that came off the internet here. So why use Cassandra? It's a multi-master system that works in multiple data centers. It's linearly scalable, allows for larger than in-memory data sets when you partition over multiple nodes. It's got very, very good performance, and we'll talk about this further later. It's fully durable. When you talk about many other databases, to get the kind of performance that you see in Cassandra, you have to turn some knobs, turn off durability, do some other stuff along those lines. In Cassandra, there's no switch to say, well, actually there is now, because we added it to sort of compare ourselves with some other people that didn't have durable rights. But by default, Cassandra is fully durable. You don't have to change anything to make your rights durable. And there's integrated caching. A lot of people find Cassandra's reads fast enough that they can get rid of things like, they can get rid of RIAC in front of it, or they can get rid of memcache in front of it. The other nice thing about it is its consistency model is tunable. We'll talk about that in a bit as well. Who is Cassandra used by? It spans most verticals that I'm aware of. The financial industry, social media, advertising. This is a list of a couple of the people that we've gone out and we've helped out as a company to make them successful with Cassandra. So who's investing in Cassandra? A lot of people ask this question. So, MySQL has Oracle support. I don't know, MongoDB has 10gen and maybe some other people out there. Who's investing in Cassandra? Well, we are. We've got 4 or 5 people who work full-time on Cassandra. Twitter is also investing heavily in Cassandra. They actually have a committer on staff. And then, of course, there's Netflix out there. I don't know if have any of you seen the presentation from Adrian Cockcroft about replacing Data Center Oracle with Cassandra? If you haven't, take a look at it. He's got an excellent story there where he talks about how his organization has replaced Oracle with Cassandra almost everywhere that they're using it today. Also, Rackspace, pretty heavily involved in the development of Cassandra. And one notable thing is that there are over 100 different individual contributors to Cassandra, which makes us one of the most active projects in the Apache ecosystem. I'd say on the order of solar. So we talked about CAP already in the previous talk. Durability is important. It's a very important part of database systems. It's important to know that when I tell the database to write the data, it actually made it to disk. So one of the things that we take advantage of is that fsync is cheap. Latency is subject to rotational latency only in Cassandra. I'll explain that in the next slide. You usually configure Cassandra to use a separate partition for the commit log. Commit log is write only, you never read from it. And it also makes one thing kind of interesting here, that you don't really benefit, on the commit log at least, from using SSDs. There are occasions where it might help marginally, but it usually won't help a lot for the commit log itself. Now on the data partition, you may see some substantial benefit there. But basically, the write path for Cassandra is very simple. As a client writes to Cassandra, basically two things happen. There's a synchronous write that happens to the commit log, and there's another synchronous write that happens to an in-memory representation of the data. And this in-memory representation of the data is where people will come in and read from before it's written out to a durable format on disk. But basically here, you've got append-only log segments. There's one at a time, and for each column family that exists over here, we might write one key from the first column family, then one from the third, one from the second. And these only exist in the case that your node goes down and needs to come back up, and we need to rebuild the in-memory representation of these column families that may not have been flushed out to disk yet. With Cassandra, the other thing that makes it very, very nice is you get tunable consistency. A lot of people talk about eventual consistency, and in Cassandra, you can choose whether or not you want an eventually consistent system or you want a fully consistent system. And Craig covered this pretty well, talking about having a certain number of replicas, or sorry, a certain number of reads and a certain number of writes. As long as your reads plus your writes are greater than the number of replicas that you have, then you can have a fully consistent system. This means that you can read it quorum, and then you can write it quorum, you can write it quorum, and then you can read it quorum, and your read will be consistent because you wrote more than, you wrote more than the majority plus one of your replicas. When you go and read a majority plus one of your replicas, you'll get a fully consistent view of your data at that point, which is a very, very important thing for a lot of people. However, if you want to tune it down and you say, I can tolerate some degree of inconsistency in my data, then you can go in and you can write consistency level 1 and read it consistency level 1, or you can write it at a quorum and then you can read it consistency level 1. Very flexible in that case, and you can tune it to whatever your use case requires. So you choose your availability versus consistency trade-off with Cassandra, which is quite nice. These are some of the consistency levels that you have in Cassandra. Because Cassandra is the spawn of Amazon Dynamo as well as Amazon Dynamo as well as Bigtable, you get some things that you wouldn't see in a Bigtable implementation. For example, you get the write consistency of any, which implies that there's this hinted handoff system, which is a way to guarantee very, very, very reliable writes. So if all of my replicas for a certain piece of data are down, I can actually write a hint in another one of the nodes on the system so that when one of the replicas comes back up, that write will be replayed to one of the other systems. It's a best effort system, but then again, you turn it on right here by saying, I'm going to allow writes at any. You cannot allow writes at any and require writes big 1, local quorum, which is an optimization for multi-data center systems, or quorum, which is the majority plus 1. Local quorum means that if I want to write to my consistency requirements for a particular data center, so if I'm writing to a particular data center, I require a majority plus 1 in that particular data center to agree before my read or write is successful. So a tunable consistency there. So if we had a Cassandra ring and we just had a single node in our ring, it would basically look like this. My range for my tokens here, I'm just going to say, are A through Z, to sort of to give us a little bit of an easier way to talk about these numbers. The real range for the random partitioner in Cassandra is from 0 to 227, and so I'm not going to deal with big numbers here because they're kind of hard to deal with. So if we were to add a node here, I could choose another token. I could create another node in the ring and choose a token of n, which is approximately halfway through